When most people think of calculus, they think of derivatives and integrals, and there's a good reason for that. Derivatives and integrals, of course, encode the physical concepts that make calculus so important. Now, in this presentation, we're finally going to look at derivatives and integrals for vector-valued functions. That's going to be a little bit anticlimactic because the computational side of things actually is fairly simple. It gets a little bit more complex when we're looking at the vector-valued differentiation rules, but they actually also have a very familiar shape. And so this will look a little bit simpler than the demanding visualizations that we have paced ourselves through in the previous presentations. However, in the next presentation, we're going to unify the visualizations and the computations to really do some physics that would otherwise not be accessible to us. So let's first knock out the computational side of things, and then let's talk about the physics in the next presentation. So, derivatives and integrals of vector-valued functions. Well, computing derivatives and integrals of vector-valued functions actually is simple because all computations are done component-wise. That should not be a surprise because we have already seen previously that limits are computed component-wise, and limits, of course, are used to define derivatives and integrals. Okay, so the interpretation of the derivative also is natural. It's the instantaneous velocity vector at the point in question. And that interpretation, of course, assumes that the vector-valued function is interpreted dynamically. That is, we assume that the function describes the motion of a particle. That's why in the earlier presentation I always talked about, on one hand, us having the trajectory, and on the other hand, us having a function that describes motion. And that interpretation is really so canonical that really it's the usual thing to do. There isn't really much else to say there. Okay, so in order to define derivatives, we need to talk again about displacements over short time intervals. So let's look at a path in space, and so this could be something that even sits in 3 dimensions, and here's the origin. And now if I want to find the instantaneous velocity at this point, what was the idea in single variable calculus? Well, I would go from the point to another point, and this, well, in single variable calculus as well as in multivariable calculus, if I were to lay a straight line through this vector, that could be called a secant line. And what we knew in single variable calculus was that if I worked out secant lines to through points that get closer to my base point, I get lines that are more and more likely, or more and more closer to being parallel to what ultimately should be the tangent line, which sits here somewhere. Well, the same thing happens here. These vectors get closer and closer to being parallel to something that would stick out like this. The only problem is those vectors are getting shorter and shorter, and so even though ultimately they become more parallel to this vector that ends up being the tangent vector, they get shorter. And well, the way this was handled in single variable calculus was that we would look at secants, which are defined as f of t0 plus h minus f of t0. So we would look at c of t0 plus h minus c of t0. And then we would divide by h to compensate for the shrinking time interval. And we would let h go to 0. And so the derivative vector ultimately ought to be the limit as h goes to 0, c of t0 plus h minus c of t0 divided by h. So it's exactly the same definition as in single variable calculus, only that we are now using vector-valued concepts, namely vector subtraction, division by a scalar, and limits of vector-valued functions. The definition, therefore, should not be a surprise. The derivative of the vector-valued function c of t at t0 is defined to be derivative with respect to time, with respect to t, which is typically interpreted as time, of c at t0 is also denoted as c prime of t0, and it's the limit as h goes to 0 of c of t0 plus h minus c of t0 divided by h. So we're back with difference quotients. Well, difference quotients were no fun to work with in one variable. They're certainly not going to become any easier when we're looking at functions that take on vectors as values, but we will very quickly go back to differentiation rules. And certainly it's defined like that only if the limit exists. And just as in single variable calculus, we will also feel free to just compute derivatives at an arbitrary point t, and then consider the derivative as a function c prime of t. So we're not going to go through too much worry about the derivative at a point versus the derivative at a function. We've done that already, and we can distinguish that in multivariable calculus just as we can distinguish it in single variable calculus. Higher order derivatives are defined as derivatives of derivatives, so just as in single variable calculus, another thing that we're not going to worry about too much. If I can compute the derivative at every point, I can figure out the derivative function, and as soon as I have a vector valued function, I can try to compute another derivative of that thing. So then in terms of dynamic concepts, in terms of the physical concepts that will fully take center stage in the next presentation, well, the instantaneous velocity at time t0 of a particle with position function c of t is v of t0 being the derivative of c of t0 with respect to t, where now t definitely is time because the position function will depend on time. And that's the same as c prime of t0. If the instantaneous speed, and now it really makes sense for us to distinguish between velocity and speed. Well, speed is the magnitude v of t0 of the velocity vector at time t0. And if we're looking at the instantaneous acceleration, well, that of a particle with position function c of t, well, that would have to be the second derivative of the position function c double prime of t0, or certainly the derivative of the velocity function. And yeah, sure, I mean, what would we say here? That the acceleration always is the derivative of the velocity because it's the rate of change of the velocity. It's just that now the instantaneous rate of change of the velocity, it is just that now our rates of change are actually vector valued. And that makes sense because we're computing rates of change of vector valued quantities. Okay, quick proposition that is going to make our computations a lot easier. If I want to take the derivative of a vector valued function c of t whose values are vectors in three-dimensional space, then that derivative is c prime of t, also dc dt. It's the derivative with respect to time of the function x of t, y of t, z of t, and it can be taken component-wise. So this derivative is nothing but the derivative of x in the x component, the derivative of y in the y component, and the derivative of z in the z component. So that means we can sidestep difference quotients and all the issues that come with them and go directly to component-wise differentiation, and that's going to be basically another reflex for when we are working with vector-valued functions. Whenever we're working with vector-valued functions, typically all operations that we know from single variable calculus, such as addition, subtraction, multiplication with a scalar, as well as derivatives, and ultimately we'll also see that that is true for integrals. All these operations are done component-wise. And that, yeah, that's x prime, y prime, z prime, certainly. The equation should be read as the derivative on the left side exists if and only if all derivatives on the right side exist. So that's the same as always. If something goes wrong here, something must go wrong over here, and vice versa. And we could also quickly say there certainly is nothing special about this happening in three-dimensional space. I could have stated an analogous result in two-dimensional space where I would have just suppressed the z's, and I could have stated an analogous result in four-dimensional space or in n-dimensional space. So the thing to take away from here, aside from the fact that we can also prove this, is that everything is just done component-wise. So, proof, well, the derivative of c with respect to t is the limit as h goes to 0, c of t plus h minus c of t divided by h. So we're looking at a time t here. I didn't stick t0s in there because that's just more typesetting and more writing. And that is the limit as h goes to 0. Well, c of t plus h is x of t plus h, y of t plus h, z of t plus h. C of t is x of t, y of t, z of t. And the division by h remains with us. And now we know with vectors everything is done component-wise. So the subtraction is done component-wise, and I could also divide every component by h. And what I get is the limit as h goes to 0 of difference quotients for the x component, for the y component, and for the z component. Limits are also taken component-wise, so I can pull the limit inside. I get the limit as h goes to 0 of a difference quotient for x, limit of a difference quotient for y, and limit of a difference quotient for z. And that's, of course, as long as everything works out, that's just x prime of t, y prime of t, z prime of t. And that is what we wanted to prove, because that was the claim. All right. As an example, if we want to find the derivative of the vector-valued function c of t being t minus 1 over 1 plus t squared, t cosine t in the y component, and e to the t squared in the z component, well, here's what we do. We take the derivative, and we know that in the x component we have to use the quotient rule, in the y component we have to use the product rule, and in the z component we have to use the chain rule, and so that's exactly what we're doing. So we get, in the x component, derivative of the numerator is 1 times the denominator, gives us the 1 plus t squared, minus derivative of the denominator, which is 2t, times the derivative of times the numerator, which is t minus 1, and we divide the whole thing by the square of the denominator, which is 1 plus t squared quantity squared. For the product rule, we take the derivative of the first, which is 1, times the second, which is cosine t, plus the first, which is t, times the derivative of the second, which is negative sine t. And for the third one, we have the chain rule. Well, we take the derivative of the outer function. The outer function is an exponential function. The derivative of the exponential function is itself, so we keep e to the t squared, and we multiply with the derivative of the inner function, which is 2t. So basically what we keep on having to do is we must be able to recall the various differentiation rules, and we'll also need to be able to recall the various integration rules, and as soon as we can do that, things are just fine. And well, once we've got that, all we can do is just simplify a little bit. We get 1 times 1 is 1. Then we have plus t squared minus 2t squared gives us minus t squared. And then minus 2t times negative 1 gives us plus 2t. The denominator stays the same. 1 cosine t is cosine t. T times negative sine t gives us negative t sine t. And e to the t squared times 2t is e to the t squared 2t. And that's that one. All right. Okay, so now that we have derivatives, we can also revisit the equation of a straight line and look at that from a dynamic point of view. And when we do that, we realize that, well, the vector equation of a straight line can be written as c of t being s plus t times v. And we can interpret that as the position of a particle at time t. And when we do that, well, then c of 0 is s, so s is the initial or starting point, right? So that thing is where the particle, where we're beginning the observation of the particle, if you will. And the derivative of c of t, well, that would be the derivative of s plus t times v, which would be the derivative of s1 through sn plus t times v1 through vn, which would be the derivative of s1 plus t v1, s2 plus t v2, and so on, because we can do the algebra component-wise. And then we realize that, of course, we can also take the derivatives component-wise, and so that derivative is just v1 through vn, which is v. And that means that the vector v really is the velocity of the particle. So what I told you about in the presentation on straight lines actually can be justified with calculus. The direction vector v really is also a velocity vector when we interpret things as a position function over time. All right, now let's talk about tangent lines. And when we try to work out what the equation of a tangent line is, well, let's just first of all think about what a tangent line ought to be. And so if we have a particle on a curved path in 2 or 3 dimensions, when that particle is no longer forced to stay on the path, then it continues instead on a straight path. I think when I was first working this out, I was watching Winter Olympics or some kind of winter sports, but if you've got a speed skater who is going around a corner and loses traction in that curve, then that speed skater will continue sliding along a straight line, and that line is the tangent line. Of course, these kinds of things can also happen in more dangerous situations, like if you are going around a corner in a bicycle and lose traction, you slide out, and that's a whole lot worse because you're not on ice. And then, of course, if you're driving and you're losing traction in a corner, that's when you all of a sudden have a ton of metal going on a tangent line in a rather dangerous way for anybody who is around. Okay, so the particle's velocity on this new straight path will be the instantaneous velocity at the time the forces were deactivated. Basically, that speed scatter that loses traction will continue at exactly that velocity, only straight on, and that's because energy is being preserved. Just because you lose traction doesn't mean you lose energy. And finally, the new path, yeah, it is tangential to the old one, because to branch off at an angle would have required other forces. Any change in direction in three-dimensional motion requires some kind of outside force. And so that means, basically, that the line L of t being c of a plus t times c prime of a is at the point c of a tangential to the curve traced by c of t. And that's something that we can also work out with an example. So we want to compute the equation of the tangent line of the vector valued function c of t being t squared 1 over 1 plus t squared at the point 0, 0, 1. Okay, now the previous panel had shown how to figure out the tangent line at a certain time t. Well, because the problem here is given in geometric terms, we must first find t2, and that's not that bad, because the x-coordinate gives us that t must be equal to 0, and then just to double check, if I plug in t equals 0 into this function, I get c of 0 being 0, 0, 1 over 1 plus 0, which is 0, 0, 1 as a vector. And, well, now we also need the derivative. Well, the derivative of c of t is the derivative of t squared 1 over 1 plus t squared. Well, the derivative of t is, the derivative of t is 1, the derivative of t squared is 2t, and the derivative of 1 over 1 plus t squared, you compute that with the chain rule, because that's 1 plus t squared to the negative 1, so the derivative is negative 1, 1 plus t squared to the negative 2 times 2t, and if you work that out, well, you get the 1, you get the 2t that I mentioned, and you get negative 1 plus t squared to the negative 2 times 2t. I only wrote it as a fraction already. We need that derivative at time t equals 0, and at time t equals 0 we get 1, 0, 0. And so that means that the tangent line is point at which we compute the tangent line, 0, 0, 1, plus parameter u. I wanted to call it u instead of t, just to also express explicitly that this is a geometric parameter, whereas this is a time parameter very often, plus u times velocity vector, which is 1, 0, 0 times c prime of 0. And graphically that also works out, because if we are to look at the picture, here is the function, here's the point where we compute the tangent line, and we can see that from any angle that we want to turn this graph to, the line really is very much tangential. And of course here we can also see that if we look at this down n axis, I think we're looking at it down the z axis maybe, or yeah, well, down one of the axes. Now that I've rotated the cube, I don't remember quite what we had there previously. I think we're looking down the z-axis though. We really get something that could also be a two-dimensional picture. So that does check out, and well, we move on, and we're going to talk about integrals. Well, the indefinite integral c of t dt of the vector valued function is the family of all antiderivatives of c of t. That is, it is the family of all vector valued functions b of t with b prime of t equals c of t. Again, what you want to do is you want to anchor as much as possible here to aid memory in things that you know from single variable calculus, and you realize this is the same definition as the definition of the indefinite integral in single variable calculus, except now we're working with vector valued functions. Then, of course, the proposition, the indefinite integral of a vector valued functions whose values are vectors in three-dimensional space are that can be evaluated component-wise. That is, the integral c of t dt is the integral x of t, y of t, z of t dt, which is nothing but integral of x of t dt in the x component, integral of y of t in the y component, and integral of z of t in the z component. So the thing to remember again is when you work with vector valued functions, you do things component-wise. And the proof here is pretty simple, because derivatives are taken component-wise. That means antiderivatives are also taken component-wise. And that's already it here. That's something you can talk your way through it a little bit more. If I took the derivative of this thing, I would take the derivatives component-wise, and I would end up with x of t, y of t, z of t, which is what the antiderivative should give us when it's differentiated. As an example, let's talk about a real physical problem. Okay, it's of course it's construed, but let's say that we flip a quarter of a 192-foot tower. Its initial velocity is 2 feet per second upward and 1 foot per second forward. We want to compute the quarter's trajectory and the time when the quarter hits the ground. Okay, disclaimer, don't do that because that quarter can reach terminal velocity, and when it then hits somebody, that's not good. I know that, or I saw a documentary where off of some high buildings in New York City, people kept flipping pennies off, and then ultimately people just said, okay, now don't do that, even though the chances are slim. You could hit somebody on the ground. So this certainly is a dangerous act. But at the same time, it is also something that allows us to really work out the kinematics, because now we have 3 dimensions. This is a problem we could have solved in regular integral calculus also, but we wouldn't have been able to explicitly take into account the forward motion. Well, I guess we could have, but basically we would have just had to simulate what we're doing with vectors anyway. And so with multivariable calculus, we can just work this out in 3 dimensions. We know that we can set the initial position at velocity as c of 0 being 0, 0, 192. So we're aligning the z-axis with the initial position, and we are 192 feet up. So that's in feet. We can set the initial velocity as 1 foot per second forward and 2 feet per second upwards. So this is in units feet per second. So we attach units to vectors just as previously also. This is 1 foot per second here, 2 feet per second here. So this is multiplied as just like a scalar. And the acceleration, well, that's something that we look up in a physics text. The acceleration is 32 feet per second squared down. And so it's, as a vector, it's 0, 0, negative 32. And the rest is just computation, right? Here's our old friend, that green box that I hope you will ultimately see with relief, because even though the computation may take some time, we know what to do from here on out. We need to integrate the acceleration to get the velocity, and then we need to integrate the velocity to get the position function, and that position function is the trajectory. So how do we do that? Well, the velocity is the antiderivative of the acceleration, which means we integrate 0, 0, negative 32 over time. And that would be, well, 0, 0 gives us 0, 0. Integral of negative 32 is negative 32t, and then we've got that integration constant in single variable calculus. Well, in multivariable calculus, the integration constant is actually a vector. It consists technically of 3 integration constants, because we need to get one for x, which is vx, we need to get one for y, which is vy, and we need to get one for z, which is vz. What we know about the velocity is that the velocity at 0 is 0, 0, 0 plus vx, vy, vz, and it's supposed to be equal to 1, 0, 2. So here we get very quickly that vx is 1, vy is 0, vz is 2, and that means that the velocity at time t is 0 plus 1, 0 plus 0, and negative 32t plus 2. We integrate that to get the position function. So c of t is the integral of the velocity, which is the integral of 1, 0, negative 32t plus 2 dt. Well, that gives us t0 and then negative 16t squared plus 2t, if we find the antiderivatives. And again, we have to put in integration constants, cx, cy, and cz. And then we take c of 0, and c of 0 is 0, 0, 0 plus cx, cy, cz. And that's supposed to be 0, 0, 192, which means cx is 0, cy is 0, and cz is 192. And our trajectory, therefore, is t0, negative 16t squared plus 2t from here. And then we have to add the integration constant, which is the 192. So that means we already have the trajectory, and now the only thing we have to figure out is the time when the quarter hits the ground. Well, how do we do that? Well, that's another thing where we just use common sense / visualization, and that is hitting the ground means that z is equal to 0, because after all the tower was 192 feet tall, and we set it up in such a way that our initial position was 192 feet, so our height for the ground is assumed to be 0. We're not assuming that the tower is surrounded by mountains and things like that. And well, that means that we need to set the z coordinate equal to 0, so we need to set negative 16t squared plus 2t plus 192 equal to 0. And when you get something like that, it's always good to see for factors that cancel, and you've got a 2 you can cancel here. So you get negative 8t squared plus 1t plus 96 is equal to 0, and then you stick that into the quadratic formula. I don't see how to factor that, and that's because it doesn't factor nicely. And so we get negative 1 plus minus 1 squared, b squared minus 4 times a, which is negative 8 times 96 divided by negative 16. And, well, if you've seen enough presentations of mine, you know that I believe in mental calculation. Yeah, this is one that I worked out with a calculator. Okay, so no playing pretend here when the numbers get ugly, even when they're integers. You work it out with a calculator. Turns out that it's negative 1 plus minus square root 3073 over negative 16. That still really isn't something that we can use in a physical problem. And when we, with a calculator, again work out the solutions are negative 3.4022 seconds and 3.5272 seconds. And, well, this solution we have to discard, because this solution would basically say that the quarter hits the ground because it's being flipped off the 192-foot tower, or the quarter has been launched to reach the position 192 feet off the ground with exactly that velocity, and there's nothing in the problem that says that. So this solution is being discarded, and that means the quarter hits the ground after about 3.5 seconds, and that solves the whole problem. Okay, when we talk about integrals, we can also talk about definite integrals, but it turns out that for vector-valued functions, definite integrals really take a back seat unless we want to use them to compute displacements, and we compute displacements typically with antiderivatives. So this is really mainly for completeness sake, namely, a vector-valued function c of t defined on AB is called integrable if and only if all Riemann sums of c over AB within subintervals and divisions and evaluation at any point tk star in the subinterval converge as n approaches infinity. The limit is called the definite integral of c over AB. Now, what were those Riemann sums again? In symbols, the integral from a to b, c of t dt is exactly the limit as n goes to infinity of b minus a over n. So you take your interval, cut it up into n subintervals of equal length, and then you just sum k equals 1 to n the vector at a point tk inside, at point tk star inside the kth subinterval. We're going to forego an example here. If you have a homework problem on that, well, you just work with the definition. That's a little demanding here because the definition is ugly, but it's not something that I think we need to spend a lot of time with. As a proposition, the definite integral of a vector-valued function whose values are in three-dimensional space, are vectors in three-dimensional space, is, well, you've got three guesses. It's computed component-wise, namely the integral c of t dt is the integral x of t, y of t, z of t dt is the integral from a to b x of t, integral a to b y of t, integral a to b z of t. So the old mantra, when you work with a vector-valued function, you work component-wise. That is something that is going to accompany us from here on out through the remainder of multivariable calculus. And again, it's the left side exists if and only if the right side exists. All right, so now we're going to finish out with vector-valued differentiation rules and some concepts that we will actually need in the next presentation. So, if you've got c of t and u of t, and they're both differentiable vector-valued function, and a is a number, then the following hold. The derivative with respect to time of a sum of vector-valued functions. Well, how did we do that with regular functions? Well, it was the derivative of c plus the derivative of u, and that's exactly what it is for vector-valued functions. That should be clear because the addition as well as the derivative is component-wise, so you do everything component-wise and then puzzle it apart again. The derivative of a scalar times a vector-valued function, well, what did we know? Scalars could always be pulled out of derivatives, and so again, that derivative should be a times c prime of t, and it is, because what you do is you put the scalar into all the components, you pull the derivative into the components, you realize that the scalar pulls out of the component-wise derivatives, and then it pulls out overall. Then we have something that talks about the chain rule for vector-valued functions. So here we're just staying with the analogs of the things that we've already seen and that have direct analogs. The chain rule for vector-valued functions is that if c of t is a differentiable vector-valued function and f of t is a differentiable real-valued function, well, then I can take the real-valued function and stick it into the vector-valued function. And the derivative of that, well, what was the derivative according to the chain rule? It was the derivative of the outer function at the inner function times the derivative of the inner function. And again, the same thing is true here. We have the derivative of the outer function, which is c prime, at the inner function, which is f of t, times the derivative of the inner function, and I put the f prime of t in front because technically scalars are always multiplied with vectors from the left. Okay, now we can also look at some differentiation rules for things that are for genuinely vector-valued concepts. The proofs of the theorems on the previous panel are really as straightforward as I talked you through them, even though that was technically, again, shadow boxing. And so if you didn't see that, then go ahead and write out a few of those proofs. They're not that bad. So we also have product rules for vector-valued functions because we can multiply vector-valued functions to each other in at least two different ways, scalar product and vector product, right? So we let c of t and s of t be differentiable vector-valued functions, and we let f of t be a real-valued function because technically we can also multiply real-valued functions with vector-valued functions. And then we have the following. The derivative of scalar function times vector-valued function is f prime of t, c of t plus f of t times c prime of t. So it's basically the same thing as the product rule in single variable calculus, only that we now have a real valued function and a vector valued function. We have to keep track of which is which. The derivative with respect to time of the dot product c of t times s of t, well, that is c prime of t dot s of t plus c of t dot s prime of t. And even though I keep the order of the factors, and that's because I just want us to pick up some good habits of mind, because for the cross product the order of the factors actually matters. Again, we see it looks like the product rule for single valued functions, and the order of the factors here also doesn't matter because it doesn't matter for the dot product. However, if c and s take values in three-dimensional space, we also have that the derivative of c of t cross s of t is c prime of t dot cross s of t plus c of t cross s prime of t, and here the order of factors must be kept as indicated, and that's because we know that when we reverse the factors in the cross product, we get an extra negative sign. Now, all these rules can be proved component-wise, and we are going to just prove the product rule for the scalar product. You can work out the other ones. The ones for multiplying with a real-valued function is actually simple, and the one for the cross product is harder. Well, what do we have? We have the derivative with respect to time of c of t dot s of t, which would be the derivative with respect to time of c1 through cn dot s1 through sn, but we know what that is. That's the derivative with respect to time of c1 s1 plus c2 s2 plus all the way through cn sn. And we can take the derivative of that, because now the derivative of c1 s1, that's just the scalar valued product rule, so that's c prime s1 plus c1 s1 prime, plus the derivative of this one would be c2 prime s2 plus c2 s2 prime, and that keeps going like that until we take the derivative of cn sn, which is of course cn prime sn plus cn sn prime. And now we can resort that. So that's c1 prime s1 of t plus c2 prime s2 of t plus all the way through cn prime sn of t plus, and now we're looking at c1 s prime s1 prime plus c2 s2 prime plus cn plus all the way through cn sn prime And that is now something we can puzzle apart again. So we know this from the previous panel, and we realize that the first is the dot product of C1 prime through Cn prime dot S1 through Sn. And the second one is the dot product of C1 through Cn dot S1 prime through Sn prime, and that's just C prime dot S plus C dot S prime. And that's the whole proof. So this is something where I want you to be able to follow these things along and maybe also work your way through a proof or two on your own. If you can't work it out left to right, typically it's a good idea to start on the left side, simplify, start on the right side, simplify, and then see that the simplifications meet in the middle. What you can also see in this proof is that if we're working with 2 dimensions, 3 dimensions, or n dimensions, the proofs are all very similar. So here you've seen an n-dimensional proof, and except for the magic 3 dots, there is really no difference between that and a 3-dimensional proof. What you have heard in the language that I've been using, it is quite customary, because there's now so much to be kept track of, that typically when people talk about these functions, they drop the arguments. And we're going to see that when we're talking about the further vector-valued differentiation rules. First of all, a little lemma that we need in the next presentation, and that is if we have a vector-valued function, and if the magnitude c of t norm is constant for all t, then c of t and c prime of t are perpendicular for all t. So that's a first application of these differentiation rules, because if we want to prove that, well, we know that c of t norm is constant, so it's some constant k. Well, if I have an equation, I can take then I can square the equation, which is what I've done here, and that just gives me that c of t norm squared is k squared, and I can take derivatives on both sides. Well, the square of the norm, we also know, is just c of t dot c of t, and this is something that I can now apply a differentiation rule to, and that's what we will do, because now the differentiation rule says this is c prime of t dot c of t plus c of t dot c prime of t. The derivative of a constant, of course, is 0, so this gives us 2c prime of t dot c of t equals 0. And that can, of course, only happen when the dot product of c and c prime is equal to 0. And that means that c and c prime are perpendicular. And because the t was arbitrary, this works indeed for all t. So that's something that we're going to use in the next presentation. We also want to look at another example of how to handle triple products that will come in handy, if not here, then potentially in the derivation of Kepler's law, which is something that we may or may not do in my class as a project. But okay, so if you've got a triple product, a of t cross b of t cross c of t, if we want to compute the derivative with respect to time t, well, that first of all implicitly, of course, assumes that everything here happens in 3-dimensional space. But yeah, that's just something that we have stored away in our minds somewhere. The other thing, as is customary, even though we may hear of it for the first time or for the second time here, we see of it in writing for the first time, we drop the argument t. So the derivative of a cross b cross c, well, we know the derivative of a cross something. So this is the derivative of a cross b cross c plus a cross the derivative of b cross c. And we know how to take the derivative of b cross c, so this becomes the derivative of a cross b cross c plus a cross the derivative of b cross c plus b cross the derivative of c. And then we can multiply out this summation, and we get the derivative of a cross b cross c plus a cross the derivative of b cross c plus a cross the derivative of b cross the derivative of c, and that is the whole differentiation formula here. So what have we done, and what have we seen? Well, we have seen some new differentiation rules. We know that as long as we have things that are concrete, things work very much as before. We just do the operations component-wise. And we have rules that basically say for all these new products, as long as we remember the algebraic rules from working with vectors, which carry over to vector-valued functions, we simply apply these rules to new sets of symbols that are now vector-valued functions, but the rules work very similar, as we have seen for this product rule, they work very similar to the rules for scalar-valued functions. And so now all that is left to do is to practice some of that by doing some homework on these kinds of differentiations of vector-valued functions. I'll see you in the next presentation where we're going to put all of this into a really neat physical context. That presentation will take a while. It's going to be demanding conceptually as well as computationally, so prepare yourself well for it by first doing a good number of examples so that this stuff comes naturally to you. I'll see you in the next one.